Engineering is a balancing act. A core task of every engineer is to balance the frequently competing requirements of time, performance, and cost. Today, however, sustainability has become a key attribute and a line item requirement for many products and processes. Dealing with this additional constraint puts a premium on engineering creativity and on the tools used for successful development. We've seen how digital technologies have become indispensable in modern engineering by exploring the life cycle of an autonomous vehicle. In this final installment, we'll examine how those same technologies can deliver that life cycle target while achieving sustainability targets as well. A common methodology is the Environmental Life Cycle Assessment, the LCA or ELCA. It's a cradle-to-grave examination of the environmental footprint of a product or service. For products, it includes use in the field and the environmental impact from the production process. It also includes the impact of outsourced components and assemblies. A typical environmental LCA consists of 4 steps. The first is setting up a goal and scope for the project. This is frequently integrated into the early definition phase of engineering product planning. A critical first step is defining a functional unit. The product, service, or system definition used to normalize all LCA calculations so results are easily comparable. In our case, we'll take as a functional unit the individual vehicle as built, driven, and ultimately recycled. The next step is the inventory analysis. It's where engineers assess all the material and energy flows in and out of the system which could have an effect on the environment. What are the direct emissions, materials, and energy consumed to produce the product and to sustain its operations and its eventual disposal? This may be the most challenging part of the LCA. As we've seen in this series, however, proven tools already exist to handle this challenge. The next stage links the data collected in the inventory analysis to known environmental impacts. To do this, the engineer needs access to libraries of emissions data that have been collected, collated, and standardized by LCA practitioners over the years. If a car door contains a stamped steel panel weighing 5 pounds, then this library will contain the environmental impact of that stamping process, including the impacts of material handling and sourcing of raw materials. In the final stage, interpretation, the environmental impacts are combined into totals and are measured against project goals. At this stage, meaningful comparisons can be made between alternate manufacturing, operation, and disposal strategies. Is it more environmentally sound to make that car door from aluminum instead of steel? This is where direct comparison of environmental impact and the cost implications of alternate manufacturing methods come into view. Where does all this fit into our hypothetical autonomous vehicle design? In this example, the design and manufacturing team has created a digital twin of its product design, as well as the production process to make it. Where jurisdictions require manufacturers to use product stewardship systems, it may include systems of disposal and recycling. The ability of MBSE, PLM, and the digital thread to form a single source of truth for the data needed for LCA is key. By coupling that data into an LCA tool, most of the hard work of the environmental assessment is completed. LCA tools that tie into PLM systems can deliver real-time updates on environmental impact as engineers iterate their designs. Essentially, environmental impact becomes another performance parameter analyzed with each design iteration. Just as a simplifying redesign may be necessary to hit a cost target, a part or process redesigned to hit a CO2 target can be driven by the same design methodologies using the same tools. Consider an electric car. An engineer can calculate the CO2 production from mining, processing, manufacturing, and recycling the materials to make battery packs. How does that number change with a different battery chemistry? Is lithium iron phosphate a cleaner alternative with acceptable performance? Could the lithium be sourced from a supplier with lower impact? Through a combination of LCA, simulation, and real-world testing, engineers can conceive, iterate, and validate designs to achieve lifetime environmental impact targets, along with time, performance, and cost requirements. Integrate individual part and assembly improvements across complex systems like automobiles, and major improvements to sustainability are possible. Sustainability adds another layer of complexity to an already complicated engineering process. Modern, software-driven tools and methodologies such as model-based systems engineering and the digital twin are no longer just a competitive advantage, they're essential for development of today's data-heavy products and services. And unlike early iterations of engineering software, the tools available in the digital age are cloud-based and accessible to everyone from small startups to multinational corporations. Because every engineering enterprise can enjoy the benefits of integrated, connected, and collaborative systems, that autonomous car may come from anyone. Will it be you?